Mars has captivated human imagination for millennia, appearing as a blood-red wanderer against the star-filled canvas of night. Ancient civilizations named it after their gods of war, recognizing something fierce and compelling in its crimson glow. Today, as our robotic emissaries traverse its alien landscapes and our telescopes peer deeper into its atmospheric mysteries, Mars continues to whisper secrets that reshape our understanding of planetary evolution, astrobiology, and our own cosmic destiny. The fourth planet from the Sun stands as perhaps the most Earth-like world in our solar system, yet its differences tell a haunting tale of what Earth might have become under slightly altered circumstances. Every grain of Martian soil, every wisp of its thin atmosphere, every frozen droplet in its polar ice caps carries information about the fundamental processes that shape rocky worlds orbiting sun-like stars throughout the galaxy. The physical characteristics of Mars reveal a world caught between familiarity and alienation, with a diameter roughly half that of Earth and a mass about 11% of our home planet. Mars presents a scaled-down version of terrestrial physics. Its day lasts 24 hours and 37 minutes, remarkably similar to Earth's rotation period. While its axial tilt of 25.2 degrees creates seasonal variations that mirror our own annual cycles, albeit stretched across a Martian year lasting 687 Earth days. The planet's distinctive red coloration stems from iron oxide covering much of its surface, essentially rust on a planetary scale that speaks to ancient interactions between rock, water, and atmosphere. Surface temperatures range from a relatively balmy 20 degrees Celsius at the equator during summer to a frigid minus 125 degrees Celsius at the poles during winter. This temperature range, while extreme by human standards, falls within the boundaries where liquid water could theoretically exist under the right conditions, making Mars a prime target in humanity's search for life beyond Earth. Mars possesses two small, irregularly shaped moons that add to its otherworldly character. Phobos, the larger and inner moon, races around Mars in just 7.6 hours, appearing to rise in the west and set in the east from the Martian surface. This rapid orbit means Phobos is gradually spiraling inward and will eventually crash into Mars or break apart into a ring system within the next 50 million years. Deimos, the smaller outer moon, maintains a more sedate 30-hour orbit and would appear as little more than a bright star to Martian observers. Both moons likely represent captured asteroids, their dark surfaces and unusual composition suggesting they originated in the asteroid belt before being gravitationally snared by Mars during the early, chaotic period of solar system formation. These cosmic companions cast weak shadows during their transits across the Sun as seen from Mars, creating eclipse phenomena that would appear quite different from the majestic solar eclipses we experience on. The geological history of Mars unfolds like pages from an ancient tome written in stone and mineral. The planet's surface preserves a record spanning over 4 billion years, divided into distinct geological periods that chronicle the transformation of an active, possibly habitable world into the cold, dry planet we observe today. The oldest terrains, known as the Nokian period, feature heavily cratered highlands reminiscent of Earth's ancient continental shields. These regions bear the scars of the late heavy bombardment, when asteroids and comets pummeled the inner solar system approximately 3.8 to 4.1 billion years ago. The presence of clay minerals and other hydrated compounds in these ancient rocks suggests that liquid water was abundant on early Mars, creating chemical environments potentially suitable for the emergence and evolution of life. Valley networks carved into these highland regions provide compelling evidence for sustained periods of rainfall or snowmelt, painting a picture of a world where rivers flowed and lakes filled seasonal basins. The transition from the Nokian to the Hesperian period marked a fundamental shift in Martian climate and geology. Massive volcanic eruptions began building the enormous shield volcanoes that dominate the planet's equatorial region today. Olympus Mons, the largest volcano in the solar system, rises 21 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. Its base could cover an area the size of Arizona, and its gentle slopes suggest prolonged periods of volcanic activity that built the mountain through countless lava flows over hundreds of millions of years. The formation of these volcanic provinces coincided with the creation of Valles Marineris, a canyon system stretching over 4,000 kilometers across the Martian equator. This vast rift valley, deeper than the Grand Canyon and longer than the United States is wide, likely formed through a combination of tectonic forces and the collapse of surface materials into underlying void spaces created by volcanic activity, or the removal of subsurface water or ice. Mars' atmospheric composition and dynamics provide crucial insights into planetary climate evolution and the processes that determine whether a world remains habitable over geological timescales. Today's Martian atmosphere is thin and composed primarily of carbon dioxide, with traces of nitrogen, argon, and other gases creating a surface pressure less than 1% of Earth's atmospheric pressure. This tenuous atmosphere cannot support liquid water at the surface under current conditions, as water would either freeze solid or boil away into vapor depending on local temperature conditions. However, substantial evidence suggests that Mars once possessed a much thicker atmosphere capable of supporting liquid water stability across significant portions of the planet's surface. The loss of this ancient atmosphere represents one of the most important unsolved puzzles in planetary science, with implications for understanding climate evolution on Earth-like worlds throughout the universe. Several mechanisms likely contributed to the thinning of Mars' atmosphere over billions of years. The planet's relatively small size meant that its internal heat dissipated more quickly than Earth's, leading to the cessation of plate tectonics and the weakening of its magnetic field. Without a strong global magnetic field to deflect charged particles from the Sun, Mars became vulnerable to atmospheric erosion through solar wind stripping. High-energy particles from the Sun could directly impact atmospheric molecules, providing enough energy to accelerate them to escape velocity and gradually strip away the planet's gaseous envelope. Additionally, the lower gravity on Mars means that atmospheric molecules have an easier time escaping to space once they acquire sufficient thermal energy. Impact events from asteroids and comets may have also contributed to atmospheric loss by literally blasting portions of the atmosphere into space during large collisions. The search for water on Mars has evolved from speculative hypothesis to detailed mapping of subsurface ice deposits and seasonal brine flows. Early telescopic observations revealed polar ice caps that grow and shrink with the seasons, leading to initial speculation about the presence of frozen water on the Martian surface. As spacecraft missions have since confirmed that these polar caps contain substantial amounts of water ice mixed with frozen carbon dioxide, representing the largest known water reservoirs on the planet today. More surprising has been the discovery of extensive surface ice deposits at mid-latitudes, detected through neutron spectroscopy and ground-penetrating radar studies. These buried ice layers likely represent remnants of past climate conditions when Mars' axial tilt was different, causing ice to accumulate in regions that are now too warm to maintain surface ice stability. Recent discoveries of recurring slope lineae, dark streaks that appear seasonally on certain Martian slopes, have generated intense debate about the possibility of liquid water activity on present-day Mars. These features appear during warm seasons and fade during cold periods, suggesting they may involve the seasonal flow of briny water that remains liquid at temperatures below the freezing point of pure water due to dissolved salt. While alternative explanations involving dry granular flows remain possible, the seasonal nature and association with potential salt deposits make liquid water a compelling explanation for at least some of these features. The presence of perchlorate salts in Martian soil, confirmed by multiple lander missions, supports the possibility that briny solutions could remain liquid under current Martian surface conditions in certain locations and at certain times of year. The question of life on Mars encompasses both the search for past biosignatures in ancient rocks and the possibility of extant microbial communities in subsurface environments. The early history of Mars, when liquid water was stable at the surface and atmospheric conditions were more clement, provided environmental conditions that could have supported the emergence and evolution of life. The discovery of complex organic molecules in Martian rocks by the Curiosity rover demonstrates that the chemical building blocks necessary for life were present on ancient Mars, though these compounds could have formed through either biological or non-biological processes. More intriguingly, measurements of methane in the Martian atmosphere show unexplained seasonal variations and localized concentrations that are difficult to explain without invoking either active geology or biological activity. The potential for existing life on Mars likely resides in subsurface environments where liquid water might persist and where organisms would be protected from the harsh radiation environment at the planet's surface. Deep groundwater systems, if they exist, could harbor microbial communities similar to the extremophile organisms found in Earth's deep biosphere. These environments would be completely isolated from surface conditions and could potentially maintain stable conditions for billions of years. The challenge lies in accessing these potential habitats, which may exist kilometers below the surface and require advanced drilling technology to investigate. Future missions are being designed to specifically target these subsurface environments using sophisticated contamination control protocols to ensure that any detected life represents indigenous Martian biology rather than terrestrial contamination. Mars' two small moons, Phobos and Deimos, offer unique scientific opportunities and practical advantages for future human exploration of the Martian system. These irregularly shaped bodies likely represent captured asteroids, providing samples of primitive solar system material that has remained largely unchanged since the early epochs of planetary formation. Phobos, in particular, presents an attractive target for robotic sample return missions due to its low gravity and proximity to Mars. Material ejected from the Martian surface by impact events may have been captured by Phobos over billions of years, potentially preserving samples of Mars that are more ancient than anything accessible at the planet's surface. Future human missions to Mars could use these moons as staging areas, taking advantage of their minimal gravity wells to store supplies and establish communication relay stations. The seasonal cycles on Mars create dynamic changes in atmospheric pressure, ice cap coverage, and dust storm activity that provide natural experiments for understanding planetary climate system. The Martian year's length, nearly twice that of Earth's, means that each season lasts approximately 6 Earth months, allowing for extended periods of relatively stable conditions, punctuated by dramatic transitions. During Southern Hemisphere summer, the southern polar cap shrinks significantly as frozen carbon dioxide sublimates directly into the atmosphere, increasing global atmospheric pressure by up to 25%. This seasonal pressure change drives global atmospheric circulation patterns and influences the formation and dissipation of cloud systems throughout the planet. Understanding these seasonal dynamics is crucial for planning future human missions, as dust storms, temperature extremes, and atmospheric pressure variations all present challenges for surface operations and life support systems. Global dust storms represent one of Mars' most dramatic weather phenomena, occasionally engulfing the entire planet in suspended particles that can persist for months. These planet-wide events occur roughly every few Earth years, though the specific triggers and timing remain difficult to predict. Local dust storms are much more common and play important roles in redistributing surface materials and influencing local weather patterns. The fine dust particles lifted by strong winds can reach altitudes of 60 kilometers or more, creating a global haze that affects surface temperatures by blocking incoming sunlight while simultaneously warming the atmosphere through absorption of solar radiation. For future human explorers, dust storms present multiple challenges, including reduced solar power generation, increased wear on mechanical systems, and potential health hazards from fine particles infiltrating habitat systems. The geology of Mars preserves evidence for ancient hydrothermal systems that may have provided some of the most favorable environments for past life on the planet. Mineral deposits associated with hot springs and geothermal activity have been identified in several locations, suggesting that subsurface heating drove active water circulation even after surface conditions became hostile to liquid water stability. These hydrothermal environments concentrate chemical energy and provide mechanisms for concentrating organic compounds, making them prime targets for astrobiology investigations. On Earth, hydrothermal systems support diverse microbial ecosystems that derive energy from chemical reactions rather than photosynthesis, demonstrating that life can thrive in environments that receive no direct solar energy. The discovery of similar mineral assemblages on Mars suggests that comparable ecosystems might have developed during the planet's more clement past. Mars' internal structure and thermal evolution provide important constraints on the planet's capacity to maintain habitable conditions over geological timescales. Seismic monitoring by the InSight lander has begun to reveal details about the Martian interior, including the thickness of the crust, the size of the core, and the physical properties of the mantle. These measurements indicate that Mars has a relatively large core compared to its total size, composed primarily of iron and sulfur. The planet's rapid cooling and loss of internal heat generation led to the cessation of the magnetic dynamo that once protected its atmosphere from solar wind erosion. This thermal evolution represents a fundamental difference from Earth, where radioactive decay and gravitational energy continue to drive plate tectonics and maintain a protective magnetic field billions of years after formation. The search for mineral biosignatures on Mars focuses on identifying chemical and structural signatures that could only have formed through biological processes. Certain types of mineral precipitation, isotopic fractionation, and organic compound preservation patterns are strongly associated with biological activity on Earth and could potentially serve as indicators of past life on Mars. However, distinguishing biological from non-biological processes represents one of the greatest challenges in astrobiology, as many supposedly unique biosignatures can be produced through purely chemical processes under the right conditions. Advanced analytical techniques capable of making these distinctions are being developed for future Mars missions, including sophisticated mass spectrometers, X-ray diffraction systems, and microscopic imaging capabilities that can characterize samples at the molecular level. The technological challenges of Mars exploration continue to drive innovations in robotics, autonomous systems, and remote sensing technologies. The communication delay between Earth and Mars, ranging from 4 to 24 minutes depending on planetary positions, necessitates high levels of autonomy for robotic explorers. Rovers must be capable of navigating complex terrain, selecting scientific targets, and executing complex experimental protocols without real-time human oversight. This technological development has applications far beyond Mars exploration, contributing to advances in autonomous vehicles, remote sensing, and artificial intelligence systems used throughout human society. Future missions will push these capabilities even further, with sample return missions requiring unprecedented levels of autonomous coordination between multiple spacecraft operating in the challenging Martian environment. Climate modeling of ancient Mars attempts to understand how the planet maintained liquid water at its surface despite receiving less solar energy than modern Earth. Various greenhouse mechanisms have been proposed to explain this apparent paradox, including dense carbon dioxide atmospheres, methane production by geological or biological processes, and warming effects from volcanic outgassing and impact events. However, detailed atmospheric models suggest that carbon dioxide alone may not have been sufficient to maintain surface temperatures above the freezing point of water, leading to proposals for additional greenhouse gases or alternative warming mechanisms. Some researchers suggest that early Mars may have experienced only episodic warm periods triggered by volcanic activity or impact events, with liquid water stability limited to relatively brief intervals separated by long frozen epochs. The comparative planetology of Mars and Earth reveals fundamental insights about the factors that determine planetary habitability and climate stability. Both planets formed in the same region of the solar nebula and initially possessed similar inventories of water and carbon-bearing compounds. However, their different sizes, distances from the Sun, and evolutionary pathways led to dramatically different outcomes for long-term habitability. Mars' smaller size led to more rapid cooling and loss of internal heat generation, while its greater distance from the Sun reduced the energy available to drive atmospheric processes. Earth's larger size allowed it to maintain plate tectonics in a strong magnetic field, while its proximity to the Sun provided sufficient energy to sustain a complex climate system. These comparative studies inform our understanding of exoplanet habitability and help identify the characteristics that make worlds suitable for life over geological timescales. Future human exploration of Mars will require unprecedented technological capabilities and international cooperation to overcome the enormous challenges of interplanetary travel and surface operations. The journey to Mars takes 6 to 9 months using current propulsion technology, exposing crews to cosmic radiation, microgravity effects, and psychological stresses of long-duration spaceflight. Once at Mars, explorers will face a hostile environment with unbreathable atmosphere, extreme temperatures, and dangerous radiation levels at the surface. Life support systems must function reliably for years without resupply from Earth, requiring closed-loop recycling of air, water, and waste products. The development of in-situ resource utilization technologies to extract water, oxygen, and fuel from the Martian environment represents a critical capability for reducing mission costs and enabling long-term human presence on the planet. The ethical considerations surrounding Mars exploration and potential terraforming efforts raise profound questions about humanity's relationship with other worlds and our responsibilities as a spacefaring species. If life exists on Mars, either in fossil form or as active microbial communities, human activities could contaminate or destroy irreplaceable scientific resources and unique evolutionary lineage. Planetary protection protocols currently guide mission design to minimize contamination risks, but human exploration will inevitably introduce terrestrial organisms and alter local environments. Some propose that Mars should be preserved in its natural state as a planetary wilderness, while others argue that human settlement represents the natural expansion of life and consciousness beyond Earth. These debates will intensify as human missions to Mars transition from scientific expeditions to permanent settlement efforts. The technological spin-offs from Mars exploration continue to benefit life on Earth through innovations in materials science, environmental monitoring, and sustainable living technology. Closed-loop life support systems developed for Mars missions contribute to more efficient resource utilization in terrestrial applications, while advances in renewable energy and energy storage support the transition to sustainable energy systems. Robotic technologies developed for Mars exploration find applications in dangerous or remote terrestrial environments, From deep-sea exploration to disaster response operation, the integration of multiple scientific disciplines required for Mars missions fosters interdisciplinary collaboration that accelerates progress in fields ranging from astrobiology to atmospheric science. Mars serves as a natural laboratory for understanding planetary processes that operate across the solar system and beyond. The planet's well-preserved geological record provides insights into impact crater formation, volcanic processes, and atmospheric evolution that inform our understanding of rocky planets throughout the universe. Dust devil formation, seasonal atmospheric changes, and polar ice cap dynamics on Mars offer terrestrial analogs for studying similar processes on Earth under different environmental conditions. The relatively simple atmospheric composition and lack of vegetation on Mars make it an ideal location for testing and refining atmospheric models that are used to study climate change on Earth and atmospheric evolution on exoplanets. The cultural impact of Mars exploration extends far beyond scientific discovery, inspiring new generations of scientists, engineers, and explorers while fundamentally altering humanity's cosmic perspective. Images of Martian landscapes, from the first fuzzy photographs returned by early orbiters to the high-definition panoramas captured by modern rovers, have become iconic representations of human exploration and scientific achievement. The ongoing search for life on Mars captures public imagination and highlights the profound questions about our place in the universe and the prevalence of life beyond Earth. Educational programs built around Mars exploration engage students in science, technology, engineering, and mathematics fields while fostering international cooperation and peaceful uses of space technology. Mars represents both our past and our future. The planet's early history may mirror conditions on the young Earth, providing insights into the environmental factors that led to the emergence and evolution of life on our home world. Conversely, Mars' present state may offer a glimpse into Earth's distant future as our sun gradually brightens and drives irreversible changes in terrestrial climate. The lessons learned from studying Mars' climate evolution inform our understanding of planetary habitability limits and help predict the long-term fate of Earth's biosphere. As humanity faces environmental challenges on Earth, Mars serves as both a cautionary tale about planetary-scale environmental changes and a potential refuge for preserving human civilization and terrestrial life. The red planet continues to whisper its secrets across the cosmic void, each new discovery adding chapters to the greatest story ever told, the epic of planetary evolution, the search for life beyond Earth, and humanity's destiny among the stars. From ancient astronomers tracking its wandering path across the celestial sphere to modern rovers analyzing its soil and atmosphere, Mars has served as a mirror reflecting our deepest questions about life, death, and the cosmos. As we stand on the threshold of becoming a multi-planetary species, Mars beckons as our first step into the larger universe, carrying with it the hopes, dreams, and survival instincts of an entire world. The whispers from the red planet grow stronger with each passing year, calling us onward to explore, to understand, and to ensure that consciousness and life continue to flourish among the stars long after our home world has returned to cosmic dust. Mars has always carried with it a sense of mystery, a whispering presence in the night sky that has fascinated humankind since the earliest days of stargazing. When ancient civilizations first raised their eyes to the heavens, they noticed the strange reddish glow of this wandering star, unlike the fixed stars or even the other planets visible to the naked eye. To the Babylonians, Egyptians, Greeks, and Romans, Mars was more than just a celestial body. It was a symbol of war, blood, and divine power. The Romans named it after their god of war, and that association has endured for centuries, shaping our cultural imagination of the planet. Yet beyond mythology and symbolism, There has always been a deeper, quieter call from Mars, a whisper that seems to reach across the void of space, urging us to uncover its secret. This whisper is not audible in the way wind rushes through trees or water laps against a shore. It is the whisper of curiosity, of longing, of the profound human desire to know what lies beyond the boundaries of our world. For thousands of years, that whisper has grown louder as telescopes advanced, as science expanded, and as our dreams of reaching other worlds became less fantasy and more possibility. Today, when we look at Mars through the eyes of orbiters and rovers, we are no longer bound to mythology alone. We are bound to evidence, data, and breathtaking landscapes that feel at once alien and strangely familiar. Mars whispers through its dry riverbeds, suggesting that water once carved its surface. It whispers through its dust storms which sweep across the planet like restless ghosts. It whispers through its valleys and volcanoes, hinting at a past that may have been far more dynamic than its current barren silence. As we listen to those whispers, we realize that Mars is not simply a dead world drifting in the vast expanse. It is a planet with a history, perhaps even a planet that once carried the breath of life. Each photograph transmitted by our robotic explorers is like a fragment of Mars's language, a piece of its long and complicated story. We see layered sedimentary rocks that speak of ancient lakes and deltas. We see the frozen caps at its poles, whispering of seasons, cycles, and the persistence of water. We see canyons so vast they dwarf the Grand Canyon, whispering of cataclysmic forces that tore the crust apart. And yet, amid all of these geologic whispers, there is another one that lingers most strongly, the possibility that Mars once, or perhaps even now, harbors life in some hidden niche. This is the deepest and most haunting whisper of all. The suggestion that humanity is not alone, that our neighbor world may have once shared the spark of biology. Listening to Mars, therefore, is not just an act of scientific curiosity. It is a confrontation with profound philosophical and existential questions. What does it mean if Mars once had life and lost it? What does it mean if it never had life at all? And what does it mean if buried deep beneath its surface microbial colonies still persist in silence? Mars whispers across time and distance, and we, standing on Earth, are learning how to listen with better ears and sharper instruments. Our rovers, spirit, opportunity, curiosity, perseverance, are not merely machines of metal and circuits. They are translators, turning Martian whispers into signals we can interpret. They grind rocks, taste the soil, sniff the atmosphere, and send back the language of Mars in forms we can analyze. Each discovery adds to the growing chorus, telling us that Mars is not merely a dusty desert, but a world that has undergone transformations, a world that once had conditions strikingly similar to Earth. The more we listen, the more we realize that Mars is not silent. It has been speaking all along, waiting for us to hear. The whisper is patient, timeless, echoing across millions of kilometers, carried on the thin winds of the red planet, and into the imaginations of those who dream of stepping foot there. Mars whispers of deserts without end, skies tinted with butterscotch hues, horizons broken by ancient mountains, and nights illuminated by two tiny moons racing overhead. Mars whispers of the possibility of human footprints pressed into its dust, of habitats built beneath its sky, of gardens grown inside domes that resist the cold and radiation. And perhaps in some future, Mars will no longer whisper. It will speak clearly through the voices of explorers and scientists who turn the dream into reality. But for now, it remains a whisper, subtle and haunting, calling us forward, daring us to cross the void and find out what stories truly lie beneath its crimson sands. When we speak of Mars, we are speaking of a planet that embodies both familiarity and alienness in equal measure. Its landscapes echo Earth's deserts and mountains, yet its conditions are unforgiving, a constant reminder that this is not our home but a distant neighbor. Imagine standing on its surface. The sky, tinged with a pale orange haze, stretches overhead, while the horizon is framed by rocky ridges and dust-filled valleys. The temperature is bone-chilling, dropping far below freezing even at midday, and the thin atmosphere provides no real protection from the sun's ultraviolet radiation. The air itself is almost unbreathable, composed mostly of carbon dioxide, with only traces of oxygen. And yet, despite these challenges, there is something hauntingly beautiful about Mars, something that feels alive with stories. The planet's surface is not static. It is sculpted by winds that drive massive dust storms, sometimes enveloping the entire globe for weeks on end. These storms are not merely atmospheric curiosities. They are part of the ongoing dialogue between Mars and those who observe it, a whisper of the planet's restless spirit. The dust, fine as talcum powder, carries with it the memory of billions of years of erosion, grinding down rocks that once lined riverbeds and crater walls. As the winds howl, they lift these particles high into the atmosphere, scattering light in ways that turn sunsets into surreal blue glows, the reverse of what we see on Earth. Mars whispers through these phenomena, telling us that even a seemingly silent and dead world is full of movement, full of rhythms and cycles that continue long after its volcanic engines cool. Its surface is scarred with craters that testify to a violent past, when asteroids and comets rained down during the early days of the solar system, shaping not only Mars but Earth as well. Some of those impacts may have delivered water and organic molecules to Mars, just as they did to our world. In that sense, Mars whispers of a shared history of a cosmic kinship between planets that formed from the same protoplanetary disk of gas and dust. If Mars whispers of rivers and lakes that once flowed, it is because the evidence is carved into its valleys and deltas. Satellite imagery shows branching networks of channels that look uncannily like dried-up river systems on Earth. These features suggest that billions of years ago, Mars was warmer and wetter, with a thicker atmosphere that allowed liquid water to remain seeable on its surface. Water is life's greatest ally, and the whisper of ancient rivers is perhaps the most tantalizing message Mars has sent us. In Gale Crater, curiosity has found clays and minerals that form only in the presence of water, whispering of long-lost lakes that may have persisted for millions of years. Perseverance now roams Jezero Crater, a place where a river once flowed into a vast lake, depositing sediments that may still hold microscopic fossils if life ever arose there. Each rock drilled, each core sample collected, is another syllable in Mars's story, another whisper waiting to be translated when those samples are finally returned to Earth. As we uncover these clues, we are reminded that Mars is not only a planet to be studied, but also a mirror in which we see reflections of Earth's own past. Billions of years ago, our planet too was shaped by intense volcanism, frequent impacts, and shifting climates. If Mars followed a similar path but diverged into barrenness, then studying it becomes a way of understanding the fragility and resilience of life itself. Mars whispers warnings as much as it whispers invitations. Warnings that climates can change, that atmospheres can thin, that oceans can vanish. It is a living archive of planetary evolution, and every rover wheel that presses into its soil is like a finger turning the pages of a very ancient book. The whispers come not in language, but in rocks, minerals, landscapes, and dust, and it is up to us to learn how to read them before time erases the traces completely. Mars also whispers through its silence, and in that silence lies a profound contrast with Earth. Our planet is alive with noise, winds rushing through forests, oceans crashing on shores, birds singing, and cities buzzing with activity. Mars, by comparison, is eerily quiet. The atmosphere is so thin that sound barely travels. Even the strongest winds would sound like a faint whisper rather than a howl. This silence is both unsettling and captivating, a reminder that we are dealing with a world stripped down to its elemental essence. For astronauts who will one day walk its surface, the silence may be one of the most profound psychological experiences. Standing beneath an alien sky, surrounded by landscapes of breathtaking beauty, and yet hearing almost nothing. The silence, however, is not emptiness. It is a whisper of time itself, of billions of years unfolding without the constant hum of biology that fills Earth. In this quiet world, the greatest voices are the landscapes themselves. Take Olympus Mons, the tallest volcano in the solar system, rising nearly 3 times higher than Mount Everest. Its sheer scale whispers of a time when Mars was geologically active, when magma surged upward through its crust, building a mountain so massive that it defies easy comprehension. But Olympus Mons is not alone. The Tharsis region hosts a chain of enormous volcanoes, whispering of forces that once shaped Mars on a planetary scale. These features suggest that Mars had a molten heart, a dynamic engine of heat and motion that eventually cooled, leaving behind frozen monuments to its fiery past. Then there is Valles Marineris, a canyon system so vast it stretches more than 4,000 kilometers, dwarfing the Grand Canyon by an order of magnitude. Its walls and floors whisper of tectonic stresses, landslides, and perhaps even water that once coursed through its depths. Standing at the edge of Valles Marineris would be like gazing into a planetary scar, a reminder of how fragile crust can be under the forces of internal and external change. Mars whispers not only through its massive structures but also through its smallest details. Dust devils that dance across the plains, carving temporary paths into the surface, frost that forms overnight and sublimates in the morning sun, tiny pebbles that may have been tumbled in streams billions of years ago. Each of these phenomena is a subtle voice in the larger chorus of Mars's history. To scientists, these whispers are invaluable clues. They help reconstruct the environmental conditions of the past, model the dynamics of the present, and speculate on the potential for the future. Mars's silence also whispers to our imagination, shaping the way writers, filmmakers, and visionaries have depicted it for centuries. From H.G. Wells' A War of the Worlds to modern-day science fiction films, Mars has been portrayed as both a threat and a sanctuary, a place of hostile aliens or a second home for humanity. These cultural echoes are not mere fantasies. They are responses to the whispers of the planet itself, which invite us to project our hopes, fears, and dreams onto its barren surface. In many ways, the silence of Mars amplifies our own voices, reflecting back to us the stories we tell about exploration, survival, and destiny. The whispers of Mars are therefore not just geological or atmospheric. They are psychological and cultural, shaping how we see ourselves in the vastness of space. When future generations finally hear the crunch of boots on Martian soil, the silence will at last be broken, and Mars's whispers will be answered by human voices. That moment will mark not only a scientific milestone, but also the culmination of centuries of listening, wondering, and dreaming. The search for life on Mars is perhaps the loudest whisper of all, but that echoes not only in laboratories and observatories, but deep in the human soul. From the moment telescopes revealed faint surface markings, astronomers speculated about canals, civilizations, and intelligent Martians. Though those early ideas have long been dismissed, the underlying question remains just as powerful. Did Mars ever harbor life? And if it did, what form did it take? The whispers of water, minerals, and ancient lakes all converge on this central mystery. Scientists today do not expect to find sprawling Martian cities or green-skinned beings waiting for us. Instead, they listen for microscopic whispers, signs of bacteria, or simple organisms that might once have thrived in wet environments. These whispers may be embedded in rocks, preserved as chemical signatures, or locked away in subsurface ice where radiation cannot reach. If discovered, even the faintest trace of Martian life would transform our understanding of the universe. It would mean life is not unique to Earth, that biology is not a cosmic accident, but a natural outcome wherever conditions are right. This revelation would change philosophy, religion, and science all at once, forcing us to reconsider our place in the cosmos. The whisper of possible life, however, is not confined to the past. Some scientists speculate that Mars might still harbor living organisms deep underground, where liquid water could exist in briny pockets insulated from the cold surface. Instruments on orbiters have detected hints of methane gas in the atmosphere, And though its origin is debated, methane is a tantalizing whisper because on Earth, it is often produced by microbes. If Mars still exhales methane, could it be the breath of underground life? The mystery remains unresolved, and the whispers are frustratingly faint, flickering in and out of detection. Yet even faint whispers are enough to keep curiosity alive. They inspire missions like Perseverance, which is carefully gathering samples that may one day be brought back to Earth for detailed study. The potential of those samples is staggering. Within them may lie the whispers of ancient microbes, preserved across billions of years. To hold such a rock in a laboratory and discover signs of life would be to hear Mars speaking clearly for the first time. But what if Mars is silent? What if no life ever arose there? That, too, is a whisper, a sobering one that reminds us life may not be inevitable, even on worlds that seem to offer the right ingredients. In that silence, we might hear lessons about Earth's uniqueness, about the delicate balance of conditions that allowed life to flourish here. Either way, Mars is speaking to us, whether through the whispers of presence or absence. For some, this pursuit is almost spiritual. The idea that a planet so close, so visible to the naked eye, might have once shared the gift of life resonates with our deepest yearning not to be alone. To listen for life on Mars is to listen for kinship, for echoes of ourselves in the vast silence of space. Each rover wheel that presses into Martian dust is not just advancing science, it is pressing closer to an answer that humanity has long hungered to hear. The technological journey of reaching Mars is itself part of the planet's whisper, a dialogue between human ambition and cosmic challenge. Getting to Mars has never been easy. It is a world that seems to test our resolve with every attempt. More than half of all missions sent to Mars have failed, destroyed by miscalculations, malfunctions, or the harsh realities of interplanetary travel. In those failures, Mars whispers a lesson about humility, reminding us that reaching beyond Earth is never simple, that space exploration is a dialogue of patience and persistence. Yet with each setback, humanity has returned, listening more carefully, building more sophisticated machines, and refining our understanding of what Mars requires. The early flybys provided the first close-up images, revealing a cratered world that looked eerily similar to the Moon. These were the first whispers that Mars was not the lush, canal-filled planet some had imagined, but a rugged, inhospitable place. Later orbiters expanded the story, mapping canyons, volcanoes, and polar caps in detail, each image adding new words to the Martian lexicon. Landers like Viking in the 1970s brought the first taste of surface exploration, testing soil for signs of life and whispering back ambiguous results that still fuel debate today. Decades later, the Spirit and Opportunity rovers gave us unprecedented mobility, whispering through their discoveries of hematite spheres and mineral veins that water once flowed across the land. Curiosity, with its advanced laboratory instruments, deepened the conversation, finding organics and confirming habitable conditions. Perseverance now continues this legacy, not only searching but preparing samples for eventual return. Each machine is more than an instrument. It is a listener, tuned to the subtle voices of the Red Planet. But the whispers of Mars are not only about science, they are about inspiration. Each successful landing captures the imagination of millions, uniting people across nations and cultures in awe at human achievement. The moment a rover's wheels touch down, we are reminded that Mars is no longer a distant myth, but a place we can reach, explore, and someday inhabit. These whispers of progress fuel visions of human missions, of astronauts standing where robots once rolled. Yet the challenges are immense. Mars whispers through its thin air, through its radiation, through its distance from Earth. It reminds us that surviving there will require technology as advanced as our dreams are ambitious. Radiation shielding, sustainable habitats, food production, and reliable transport are all part of the whispered challenge. Each problem solved will bring us closer to Mars, and each solution will echo back home, advancing technologies that benefit Earth as well. Mars, then, is not only whispering its own story but also helping us write out. The very act of trying to reach it shapes our trajectory as a species, whispering of a future where humanity is no longer confined to a single planet. Every successful mission tells us the same thing in different words. Mars is waiting. It has been waiting for eons, whispering through its dust and stone, inviting us to listen closely enough to finally step across the gap. Mars whispers most clearly when we study its climate, for it tells us not only about itself but also about the fragility of planetary environments. Billions of years ago, Mars may have been strikingly Earth-like, with a thicker atmosphere, warmer temperatures, and liquid water flowing across its surface. The evidence lies in the networks of valleys, the presence of delta formations, and the mineral deposits that form only in watery conditions. Yet something happened, something catastrophic enough to strip Mars of its once promising climate. The planet lost most of its atmosphere, and with it went the protection against cosmic radiation and the ability to retain surface water. Today, Mars is a cold desert with average temperatures far below freezing and atmospheric pressure so low that liquid water instantly evaporates or freezes. The whisper here is not just about Mars. It is about what can happen to planets when conditions change. Scientists believe the loss of Mars's global magnetic field played a crucial role. Unlike Earth, which is shielded by a strong magnetic field generated by its molten core, Mars's dynamo shut down billions of years ago. Without this protective barrier, the solar wind gradually stripped away its atmosphere, atom by atom, leaving behind only a thin, tenuous layer. The MAVEN orbiter has confirmed this ongoing process, showing how the solar wind still strips atmospheric particles into space. Mars whispers of vulnerability, of how even a planet that once had lakes and perhaps oceans can be reduced to an arid wasteland. For humanity, this is more than a scientific curiosity. It is a warning. Our own planet's climate is changing rapidly, driven by human activity. And while Earth has a robust magnetic field, the lesson of Mars is that no planetary environment is guaranteed eternal stability. Studying Mars's climate evolution gives us a glimpse into possible futures, into what happens when greenhouse gases rise or when protective systems fail. Yet, within this whisper of loss, there is also resilience. Mars still has polar ice caps composed of both water and carbon dioxide. It still experiences seasons with frost forming in the winter and receding in the spring. Dust storms, while hazardous, are also part of a living climate system, showing that the planet is not entirely enough. The whisper, then, is twofold. Mars is both a planet that has suffered collapse and a planet that continues to breathe, however faintly. Scientists analyze its atmosphere to understand these cycles. How carbon dioxide freezes at the poles and sublimates back into gas, how dust influences temperatures, how traces of methane flicker unpredictably. Each of these patterns is a quiet message about how planetary climates operate under extreme conditions. By listening carefully, we not only reconstruct Mars's past, but also learn lessons from managing Earth's present and planning for humanity's future beyond Earth. If we dream of living on Mars, then these whispers of climate are perhaps the most important to understand, because they tell us what it will take to survive. Mars will not adapt to us. We must adapt to it, and its whispers are the guide to doing so. As we continue to listen, Mars whispers not only through science, but through the deep pull it exerts on human imagination and destiny. The red planet has always been more than just a subject of research. It has been a canvas for dreams. From ancient myths to modern cinema, Mars has served as a mirror reflecting our hopes and fears about life beyond Earth. The very color of Mars, that rusty red visible to the naked eye, seems to ignite the human imagination. It is the color of blood, fire, of danger and vitality, a color that stirs emotion and makes Mars impossible to ignore. This emotional whisper has shaped centuries of speculation. In the late 19th and early 20th centuries, astronomers like Percival Lowell believed they saw vast networks of canals on Mars, interpreting them as signs of an advanced civilization struggling to survive on a dying world. Though we now know those canals were illusions, the whisper of possible intelligence gripped popular culture, inspiring countless stories of Martians and interplanetary contact. Even after science dispelled these illusions, the whisper did not fade. It simply evolved. Mars became the stage for fictional invasions, colonization tales, and survival epics, from H.G. Wells's The War of the World to Ray Bradbury's Poetic of the Martian Chronicles. Each story reflected the cultural anxieties of its time, yet all were responses to Mars' constant whisper. There is something here worth imagining. Today, the whisper continues, but now it is joined by the real voices of scientists, engineers, and visionaries who see Mars as humanity's next great frontier. Figures like Elon Musk and organizations like NASA and ESA speak openly of sending humans there, of building bases, of making Mars a second home for our species. These are not idle fantasies, but plans backed by technology already in development. The whisper of Mars has grown so loud that it drives billion-dollar projects, international cooperation, and bold announcements that humans may walk its surface within decades. This whisper is not just about exploration. It is about survival. Earth faces many threats, from climate change to potential asteroid impacts, and Mars whispers of continuity, of becoming a multi-planetary species. The whisper suggests that our destiny is not to remain confined to one fragile world, but to expand outward, carrying life into the cosmos. For some, this is a grand vision. For others, it is a necessary insurance policy. Either way, the whisper resonates deeply, tugging at both our sense of wonder and our instinct for survival. Mars is not asking us to come. It is not a sentient being with intentions, but its very presence, so close and yet so different, whispers an invitation. The whisper says, here is a place you can reach, a world that challenges you but does not make it impossible. Unlike Venus with its crushing heat and toxic skies, or the outer planets with their immense distances, Mars is within grasp. It is difficult, yes, but not beyond imagination. That is why the whisper of Mars is louder than any other planet. It speaks not only to our minds, but to our hearts, telling us that the next chapter of the human story could unfold beneath its red sky. In this way, Mars becomes more than a planet. It becomes a destiny, a goal, a companion in our journey through the cosmos. The whisper is there every time we look up at the night sky and see its red glow. Every time we marvel at rover images, every time a rocket launches with Mars as its target. It is a whisper that grows stronger with each passing decade, and soon, perhaps within our lifetimes, it will become a conversation spoken not just by machines, but by human voices on Martian soil. In the end, Mars is more than a world of dust and stone, more than the sum of its canyons, volcanoes, and polar caps. It is a presence, a constant whisperer in the story of humanity. For thousands of years, it has hovered in our night skies, glowing red like a beacon, and we have woven myths, fears, and dreams around its. With the birth of science, those dreams began to sharpen into questions, and those questions gave rise to missions, machines, and discoveries that continue to this day. Every rover wheel pressed into its soil, every satellite that traced its orbit, every experiment that tasted its atmosphere, all of these have been part of a conversation with a planet that does not speak but nonetheless tells its story in silence. Mars whispers of rivers that once flowed, of climates that once supported possibilities, of a past that may have been hospitable to life. It whispers of volcanic titans that reshaped its crust, of colossal canyons that tore its surface apart, of winds that still race across its plains and paint the sky with. It whispers of loss, of the vanishing of oceans and the thinning of air, of a transformation from a potentially fertile world to a frozen desert. But within that whisper of loss lies also a whisper of promise that the planet endures, that traces of water and perhaps even life might still be hidden in its depths, that its surface awaits the touch of human hands. For scientists, Mars is a teacher, offering lessons about planetary evolution, about climate fragility, about the forces that shape worlds. For dreamers, it is a stage upon which the future of humanity may unfold, a world where the first steps beyond Earth might be taken. For all of us, it is a mirror, reflecting our curiosity, our resilience, our hunger to go further than those who came before us. Mars whispers not in words, but in the language of landscapes, in the silence of its deserts, in the faint signals caught by antennas millions of kilometers away. And we, in turn, whisper back. Through the voices of engineers building rockets, scientists analyzing data, children gazing at the sky and imagining what might. The conversation grows richer with every year, and soon it may reach a new chapter when the first human voice carries across its thin atmosphere. Perhaps those voices will speak of discovery, of wonder, of the strange beauty of a sky where sunsets glow blue and two moons race across the night. Perhaps they will speak of survival, of struggle, of learning how to build homes in a place that does not welcome us easily. Whatever they say, those voices will mark the moment when whispers become dialogue, when Mars ceases to be only a dream and becomes a lived reality. And beyond Mars, the whispers of other worlds will call to us. Europa, Titan, Enceladus, and the countless exoplanets that dot the galaxy. But it will be Mars that we remember as the first, the world that whispered the loudest, the neighbor that drew us across. As we close our eyes and imagine that red glow in the night sky, let us remember that Mars's whispers are not faint. They are persistent, timeless, and patient. They remind us that the universe is not silent, that it speaks in the language of stars and planets waiting for us to learn how to listen. To heed Mars's whispers is to honor our own restless spirit, the part of us that has always longed to journey into the unknown. The red planet will continue to glow above us, whispering of what was, what is, and what might yet be. And in answering that whisper, humanity may find not only a new world, but a new understanding of itself.